on Dr. Punam Kasturi now. Should I switch off mine?
No, ma'am, just a second.
Yeah, here it is. Okay, good. So it's a pleasure for me to introduce Dr. Punam Kasturi again. She did her graduation in 1992, post-graduation in 1994, and PhD in 2008 from University of Delhi. She is presently working in the Department of Electronics, Deen Dayal Upadhyay College, University of Delhi. She has more than 22 years of teaching experience in digital electronics and VHDL design. She is currently associate professor there, and she has conducted 7 workshops and training sessions in the area of digital design, VHDL programming, and Vivado design flow. So welcome, Dr. Punam. I'm glad you're back here with us. And so we are eager to listen to the numericals that you're going to base upon your previous lecture. Dr. Savita, kindly stop sharing your slide so that she can start sharing her slide.
Thank you so much, Dr. Punita. Thank you for giving me the opportunity to meet again and interact again with the students.
We will give you many opportunities, Dr. Punam. I still have a plan of covering all CBCS syllabus electronics papers with you, which are based FPGA and all those SEC papers.
Yeah, that I can take very easily. Yes, sure.
So
anytime.
we shall meet again. Yeah, please.
Sure. Good evening, students, and I am back again to interact with you, and I'll share my screen. Today, I'll be focusing only on the problems based on the topics that I had covered, and the topics that I had covered were basics, number systems, and combinational circuits. So today we'll see certain questions that have already come in exams and how to handle those questions. So normally the kinds of questions that you attempt in number system are converting from one base to another, then back to addition, subtractions, two's complement, and so on. Certain typical questions of number system are of this kind, like say determine the value of base x if 321x is equal to 441 in base 5. So the base value is now to be determined given that this number is equal to 441 in base 5. So how to go about it? So the method is same, that following the logic that we have been using. So the expanded form is used. So 321 is expanded in x, 3 into x square plus 2 into x to power 1 plus 1 into x to power 0. And similarly, 441 is also expanded in the powers of 5. That means this is also now in base 10 and this is also now in base 10. This is the equivalent. So now this becomes nothing but like your algebraic equation, which is polynomial. So you reduce it, simplify it the way you do in your mathematical algebra. 3x squared plus 2x minus 120 is equal to 0. And find the roots of this equation. So once you see that when we are finding the roots of the equation, the possible solutions could be positive or negative. Now we cannot have a negative base, so we have to rule out that number. And when you solve this number, the x comes out to be 6. So it clearly tells us that 321 in base 6 is equal to 441 in base 5. So what we have followed is nothing but the simplest of the logic, that we have expanded both the numbers into decimal and equated them, because this also represents the same decimal number and the second one also represents the same decimal number. Am I audible? Hello? Hello, Dr. Punita.
Yeah. Yes.
There's some bell sound coming in between.
Just a second. Let me see. Maybe somebody's audio has switched on. Give me
Okay,
a second, please.
okay. So I continue.
Ma'am, actually, if
Yeah,
sometimes,
please.
yeah,
If students join, then also there
then
is a beep sound in Zoom.
Okay,
If they join, if somebody gets disconnected and joins again, there'll be a bell to
oh,
tell you
that
that
ting
somebody
ting.
is
Okay,
entered.
okay. Okay, so I continue with my concepts. So what we are basically doing, we are simply expanding this number into its equivalent decimal 10, expanding this number into its equivalent decimal base, and then finding out the x value with the help of the mathematical algebra systems, keeping in mind that the roots of the equation, if they come out to be negative, they are of no use to us. So we'll discard those roots and only the positive values will be retained. This was one question. Next we have on the same lines, if 137 plus 276 is 435, the base is not given, an equation is given, and we can clearly see that this is not a in the decimal system. So 137 plus 276 is equal to 435. Now you please see that whenever I'm reading these numbers, I'm just reading the face values. I'm not reading the weights. This is not 137. This is not 276. And so this is also not 435, because this is not in base 10. So this is 137 plus 276 is equal to 435. So some equation has been given, but it is not clear. It is not known that what is the base of these three numbers. But what is being asked, if this is so, then how much is 731 plus 672? So that means we basically need to find out the base of this equation, the base of these three numbers. So considering 137, then x plus 276 in base x is equal to 435 in base x. So all the three numbers will be in the same base system. Now x is certainly higher than 7, right? Because 7 is the highest digit or the highest symbol that we can see in this equation. So if 7 is a symbol in base x, that means this base x has to be 8 or higher. It cannot be less than 8. Why it cannot be less than 8? Say if you have a base 7, that means radix is 7, then the symbols that you have are from 0 to 6. These are the 7 symbols that we will be using. But since in this equation we have the symbol 7, so the base of this equation has to be certainly 8 or higher. Now, taking the units place first, we add 7 plus 6. Why? Because whatever is the base, it is higher than 7. So that will be, as long as your base is 9 or less than 9. All the basic symbols, if you will convert them to decimal, they will have the same meaning. So any number, any base from certainly not 0, base 1 to 9. So we basically start from this base from 2 to onwards. So if your base is going from 2 to 9, then your symbols will go from 0 to 8 only. That means if you will convert these symbols from 0 to 8 into decimal, you'll get the same numbers. In fact, if you go on into any other higher system also, like we have done hexadecimal system, we have basic symbols which are 16 in number. And these basic symbols go from 0 to F, right? So they go from 0 to F. So from 0 to 9, they are same as in decimal. The difference starts from A. Now here A or B or C is not there. That's okay. But even if I go in a system which is higher than the decimal system, the basic symbols from 0 to 9 will have the same representation as in decimal or in any other base. So when you add 7 plus 6, now I have actually converted them into decimal. So 7 plus 6 is now 13. Now, if it was decimal system, then 3 would have been at the units place and 1 should have gone to the next place. But since in the answer we do not have 3, what we have 5. That means this 13 has to be divided by that base, which will give a remainder of 5. So if I divide 13 by 8, then I get a remainder of 5. So this indicates that the base of this equation is 8. If we know the base of the equation, once we know this base of the equation, we can very easily now do this calculation. 731 plus 672. So doing this in base 8, 1 plus 2 gives us 3, 3 plus 7. So now at every place value, what we are doing, the basic symbol in octal converted to decimal, we do the addition and then come back, convert that answer back into the octal. So 1 when converted to decimal gives you a 1. 2 when converted to decimal gives you a 2. So if you do 1 plus 2 in decimal, we get an answer 3. And if you bring back 3 from decimal to base 8, you get back 3 only. Right? So 3 is represented as 3 only in the octal base. So here what comes? 3. We come to the next place value, 3 and 7. 3 in octal is same as 3 in decimal. 7 in octal is same as 7 in decimal. So when we add them, 3 plus 7, we get 10, which is in decimal. So this 10 in decimal has to be converted into octal. This 10 is in decimal. How will 10 in decimal be converted to octal? So you have to divide this 10 by 8. That is the steps. But if I just simply go by the logic behind, we know that if I will take out a carry from this 10, that carry will go to the next place value, and what will remain at that place is the remainder. So this quotient goes as a carry to the next place value. So 1 here, and this remainder remains at that place value. So 2 remains here. Now coming back to the next higher significant place value, here we have 1, 7 and 6. So all these symbols in octal when converted back into decimal give me the same symbols. So in decimal, when we add 1 plus 7 plus 6, we get 14. This 14 is to be now converted into octal again. So I know that I have to take a carry out from here to give it to the next place value. So minus 8. And what remains back is 6. So 6 remains at that place value, and 1 goes as a carry to the higher place value. So this way we add 731 in octal with 672 in octal, and the answer is 1623 in octal. Now coming to the next question, which is based on your Boolean algebra. A Boolean function f of two variables x and y is defined as follows. So now what they are doing, they are giving you the function. Now instead of giving it as a truth table, they have given it in a different representation format just to confuse. Right? So but what is this? When input is 0, 0, when input is 0, 1, when input is 1, 1, the output is 1. So if you'll convert it into truth table, this becomes 0, 0, 0, 1, 1, 0, 1, 1. Output is 1 for these three terms, 0, 0, 0, 1 and 1, 1. So output is 1 for here, 1 for here and 1 for here. And it is 0 for input 1, 0. So it is 0 over here. Now we have to tell what? Assuming complements of x and y are not available. A minimum cost solution for realizing f using only two input NOR gates and two input OR gates. This is only what we can use, and each of this gate has a cost of unit cost. So what will be the total cost? That means we basically need to find out how many two input NOR gates would be required and how many two input OR gates will be required. The total number will become the cost because each unit is having a unit cost. So now it's nothing but a simple, either you express it in SOP or POS form. I see that it is convenient to express it in POS form because it straight away gives me the answer. So I'll take that input sequence for which the output is 0. Represent this if the variables are x and y. So this is x variable, this is y variable. So what happens? This becomes x complement plus y. So the function is represented by f is equal to x complement plus y. Now what we have, we do not have complements. That means I need something gate to generate x complement. We do not have NOT gates. So two input NOR gates or two input OR gates are there. Now a NOR gate, if both the inputs are joined together, it behaves like a NOT gate. This is what we know. NOR is a two input gate, but if both the inputs are tied together, the output will be the inverse of the input. How is it so? NOR is x plus y complement. If x and y are the two inputs to a NOR gate, right? If this is x, y, these are the two inputs, then NOR gate will be represented as x plus y. Now, if both these are same, that means y is also x, then this becomes x plus x. And when you take its complement, x plus x, this is a logical expression and not a algebraic expression. So this remains x. So this is a Boolean expression. X plus x is still x. So complement. That means NOT gate can be implemented using a NOR gate. So to generate x complement, we need one NOR gate. And we need one two input OR gate to generate x, this x complement plus y. So in total, we need two gates. So the answer is 2 units because each gate costs a unit cost. So we require 2 units. So the answer is D. If you have any doubts related to any question, please let me know then and there only. Then coming to the next question. In the figure shown, the output y is required to be AB plus CD complement, right? Now, what should be the gates G1 and G2? They have given options. Now, we need to generate what? We need to generate y is equal to AB plus C complement D complement. Actually, it should be C complement D complement. Right? So, what are we generating over here? This is giving us C plus D. This is a NOR gate. Now, since we only have two gates over here, and if I see y, it is what? It is an OR operation of two inputs. So G2 has to be an OR gate. So G2 has to be an OR gate. And if I see this expression, C plus D complement, apply De Morgan's, and this is C bar, D bar. Since these are, I think, photocopied or something like that on the website. So this is coming out as CD whole bar, but this is actually C bar D bar. Now we need to generate AB, and that should be the output of gate 1. From here we need to generate AB. Now if the inputs are inverted, that means what we are getting here is A complement, B complement. So which gate will be generating AB? It is the NOR gate, right? If the inputs to the NOR gate you will complement, the output will be, say if this is X, Y, Z. So NOR gate is X complement plus Y complement, since we have already added a inverters. So you will be applying your De Morgan's theorem, and this will give you X dot Y. Right? So this gate should be NOR and the second gate should be OR. So A is the correct answer. Next we have a function f, which is of 3 variables A, B, C, and it is defined by as an sum of products. No, it is defined by 3 Boolean variables when expressed as sum of products is given by this expression, where A complement, B complement, C complement are the complements of the respective variables. Product of some form of the function f is, right? So what is the question? The question is that we are given a expression in SOP form and we have to find its POS form. As I said, simply taking a De Morgan's, many websites say that to convert SOP to POS, just take the De Morgan's of the function, which is not right, right? So we have to see. This function is given in the canonical form. We can see that all the 3 terms are having all the 3 literals, A, B, C. All of them have this. So this is f is expressed in your canonical form. That means if I converted it into the minterm expression, summation of minterms, now I'll read straight away from here. This is 0, 0, 0. A bar, B bar, C bar is 0, 0, 0. So this is minterm 0. Then this is 0, 1, 0. So this is minterm 2. And the third one is 1, 0, 0. So this is minterm 4. Now we need to find out what are max terms. So the terms which are not expressed are max terms, and they are 1, 3, 5, 6, and 7. Now we see there are 5 max terms. So the first 2 cases are straight away ruled out. They cannot be the answer. They are having only 3 max terms. So 3 is not possible. There are 5 max terms. So now we have to look for the answer from these 2. So one way is that you completely write it. The other way is to find out, to eliminate one of them. So if I can somehow see 0 to 4 in any of these 2, then that is not the expression for POS. How will 0 be represented? Right, 0 in max terms will be A plus B plus C. Right, A plus B plus C. This B term is having this 0 as a max term, which is a min term. So that means D is also not the answer. So in any case, C is the answer. You can verify it also by expanding these max terms. So, but quick way to save your time in competitive exams when you have to choose from an option, rather than solving the complete and getting the answer, it is much better to reach to the answer which is your correct answer, because nobody is asking you. These three are not there, that is for sure. So this is the correct answer. Yes, for practice purpose, you can go and check that 1, 3, 5, 6, 7 will be expressed like this, and this is that answer. This is 1, 0, 0, 1. This is 3, 0, 1, 1. This is 1, 0, 1, 5. And this is 6, 1, 1, 0. And the last one is 7, 1, 1, 1. So in max terms, when a variable is having a value 1, it is represented by the complement. And when a variable is having a value 0, it is written by the true form of that variable. If anyone has any doubt still here?
Ma'am, one of the students, Abhiram Singh, has asked that please say again about 8, why we choose this.
This fifth question only?
I don't think so. I think he has written in the starting. Abhiram, can in question number 2, ma'am.
Okay. In question number 2, what is okay, why
Asking-
did we chose 8?
Yes, this is the question.
We chose 8 because when we will be adding these two numbers in base x, how will we be adding them? From x we have to convert them to decimal. So from this this number 7 in base x, when you will convert this to decimal, it will be 7 in decimal. Similarly, this 6, when you will from base x convert it to decimal, it will be 6 in decimal. So in decimal, we know 7 plus 6, we can add, the answer is 13. Right? But this 13 has to be converted back into this base x, isn't it? That means from this, I have to take out a carry of that value such that the remainder is 5. Right? Such that the remainder is 5. So I can see that either I say from 13, I subtract the carry of a value 8, then only the remainder will be 5. You can try other numbers also, but in any case, 7 or less than 7 is not feasible because we are already having the symbol 7. So we have to start from 8. So here in this particular case, the very first 8 gives me the right answer. So if you take out a carry from 13 of base 9, so you'll give the carry and the carry will have a weight of 9. So that will be subtracted from here, which is nothing but like dividing 13 by 9, and the answer will be 4. So what will remain at the units place? A 4. But the problem says, the question says that what remains at the units place is 5. And this remainder at the units place I'm getting with 8. So I need not go to any higher higher base systems. So 8 is the base that I'm considering. Either I say I carry, subtract the weight of this carry, or I equivalently say divide it by 8 so that the remainder is 5. Both the things are same. When I divide it by 8, the quotient goes as a carry to the next place value. Whatever remains, that remainder remains at that place. So just by checking this units place, I am getting this 5. You can cross check that if you will add 137 and 276 in base 8, the answer should come out to be 435. But in the examination point of view, the objective is not to validate this equation. The objective is only to find x because there time is a crucial factor. But yes, right now we can cross check whether it is coming or not. So let's add 137 in base 8 with 276 in base 8. Right? So let's add these two numbers. See, if you're adding any two numbers in any other base, the methodology is that we add the digits place by place, as we do in your decimal system. Now we do not know the addition steps in octal, or to say in binary, or base 3, base 5, base 12, or so on. So what is the standard procedure is that each digit, each digit, 7 and 6, both these digits are converted to decimal. So 7 in octal is same as 7 in decimal. So this is 7 in decimal. 6 in octal is same as 6 in decimal. So this is 6 in decimal. So 7 plus 6 in decimal is 13. And when 13 is converted into octal, we divide it by 8. So this quotient goes as a carry to the next place, and the remainder remains at that place value. Now coming to the next place value, we have 1 plus 3 plus 7. These three are numbers in your base of 8. Convert them to base 10. They remain the same digits. So 1 plus 3 plus 7 in decimal is 7, 3, 10, and 1, 11. From 11, we have to take out a carry. That means you again do this process. So you divide 11 by 8. So once, this is just to visually put the things in your mind, but this division is actually not required. This is all mental division. This should be right. So we are basically subtracting this 8, and what is left behind is 3. The remainder is 3, and this quotient goes as a carry to the next place value. So this 1 comes here, and what remains here is 3. 1, 1, 2. From octal, you convert it into decimal. You have 1, 1, 2. So 1 plus 1 is 2, 2 plus 2 is 4. 4 from decimal, you convert it back to octal, which gives you again a 4. So you see, you get back the answer. So right now it's okay just to understand the concept to do it. But from the examination point of view, when you are attempting questions, and time is a crucial factor over there, I think units place is sufficient enough to check what should be the base of this equation. Once you know the base of the equation, then you can add the two numbers which are desired, and the answer can be generated. So is the point clear? Divya, are there any more questions?
No.
Okay, so I move further then. How many gates would be required to implement the following Boolean expression before simplification, right? So we are not simplifying. We have to implement this as it is. So we can see 1 OR gate, 2 OR gate. So we require 2 OR gates, which are 2 input. We require 2 input OR gates, which are 2 in number. Then we require 1 AND gate, 2 AND gate, and this is 3 AND gate. So we require 2 input AND gate, 3 in number. And then we require finally 1, 2, 3 input OR gate. So we require 1 3 input OR gate. So the total number of gates required, here it comes out to be 6. There is no such option. So what will you say? Is the question right or the question wrong? Can you write the answer in the chat box? Divya, please tell me. I'll give them 20 seconds. That what should be the answer?
I'm watching the chat box.
Okay, so just ask, I'm asking all the students to give their guess what should be the answer. What we evaluated, calculated is 6, and it's not one of the choices. So what should we do?
So Abhiram says we can reduce. Chirag says 7.
Okay, so 5 and 7 are the 7. Okay, can anyone tell me what is the reason to say 7, or it's just hypothetical कि कम कर दें या ज़्यादा कर दें, जो भी closest है. 6 के closest 5 भी है, 6 के closest 7 भी है.
Dr. Punam?
हाँ जी.
We have many students from South India, so I request you not to use Hindi. I don't know whether they would understand the language.
Okay, okay. So my question is that the question that by calculating what we have come to the number is 6, and 6 is not one of the options. What should we do? Should we go to the closest, which is 5, or we should go to 7? Many of the answers I think have come out 7.
7, somebody says 3, somebody says 5.
Okay.
Then Chirag says 2 input or gate in place of 3 input.
Yes, that's right. Right. So the right answer is 7. Why is the right answer 7? Because 2 plus 3, 5 gates are clear. All these 5 gates are 2 input OR gates or AND gate. The issue is with a 3 input OR gate. Right? So this 3 input OR gate can be implemented using 2 input OR gates. So if I have this, so a 3 input OR gate will actually require two input OR gates. So 5 plus 2, the correct answer will be 7. And how is it so? So this is A, B, and C. So this will give you A plus B. And to this further, we can do A plus B plus C. So the 3 input OR gate can be implemented using the associative law. So this is basically we are using the associative law on the 3 input OR gate. So therefore 5 are clear gates that we need. The sixth gate that was which was required as a 3 input OR gate, since it can be implemented using two input OR gates, so the right answer will be 7. So the right answer will be 7. Okay. Then I come to the next question. For the Carnot map given below, the simplified Boolean function is. Now again, I would say to save time, it is better to reach to the option rather than completely finding out the answer. So we can see that what groupings can be formed is 1. This is the second group that we can form. And the third group will be that means we have 2 groups which are of 4 cells and 1 group which is of 2 cells. Right? If it was your subject exam, then of course you are supposed to write the answer. But here you have to choose a option. And we know when we make a group of 2 cells, 1 variable is dropped. When we make a group of 4 cells, 2 variables are dropped. And when we make a group of 8 cells, then 3 variables are dropped. So this option which is having B, a single variable, this option which is having a single variable, that means this is representing a group of 8 cells. And we do not have any such group of 8 cells. So these two are ruled out. This D option is giving all the 3 terms as groups of 4 cells, which is also not true. We have 2 groups of 4 cells and 1 group of 2 cells. That means 2 terms we should have which should be having 2 variables, and 1 term we should have which should be having 3 variables. So this option is also ruled out. So the correct option is this. I am not focusing on, I have not tried to find out what are these options, but just by eliminating the 3 things, I reached to this. But let us cross check whether the given answer is correct or not. So if I first consider this group, this is A complement, B complement, and here it is A, B complement, right? This is 0, 0, and here it is 1, 0. And this is 0, 0. C complement, D complement. So for these 4, and this is C complement D, that means this is 0, 1. So A is changing its value and D is changing its value. B is 0 and C is also 0. So this becomes B bar D bar. B bar C bar. D is changing its value, right? So 0, 0, 0, 1. D is changing its value. So the pink term is B bar C bar. Then coming to these 4 corners, A bar B bar, A B bar, C bar D bar, C D bar. So A is changing its value, will be dropped. B is common, which is B bar. C is changing its value, which is dropped. D is common, which is having D bar. So B bar, D bar. Then coming to this purple term, which is a group of 2 cells, A bar, B bar, A bar, B. So B is changing its value. So it is A bar. And this is C, D bar, because this is 1, 0. C, D bar. So C, D bar. So this is the correct answer. So instead of actually writing all the expressions, I can straight away simply rule out, okay, this is not possible, this is not possible. So this is the right answer. This way you save on time. Coming to the next question. The point P in the following figure is stuck at 1. The output F will be what? Right? So here it is 1. We are not given what is B. We are not given what is C. We are simply given that this point somehow is stuck to 1. Maybe because of some fault over here. So if this point is stuck to 1, what will be F? So this is what? Nand gate. If Nand gate, both inputs tied up, it will behave like a NOT gate. So if this is 1, this input is 0. This is also this, okay, I'll label them 1, 2, 3, 4, 5, 6, 7, 8, and 9. So output of gate 5 is 0. Gate 7 is also a NAND gate. And if one of the inputs to a NAND gate is 0, what is the output of that NAND gate? It is 1. Right? NAND gate truth table is 0, 0, 0, 1, 1, 0, and 1, 1. It is 1 for these 3 cases and 0 for this case. So if one of the inputs to the NAND gate is 0, either this or this, In any case, your output will always be 1. So that means output of gate 7 is 1. So irrespective of whatever is 6 output, output of gate 7 is 1. Now, gate 8 is also a NAND gate. If one of the inputs to the NAND gate is 1, then how does the NAND gate behave? NAND gate behaves like a NOT gate. If one of the inputs to this NAND gate is 1, right? If one of the inputs is 1, then what is the relationship of the output to the other input? If this is 0, output is 1. If this is 1, output is 0. So if at gate 8, if one of the inputs is 1, then output is complement of the second input. Here we have A. So this is A complement over here. Gate 9 is also a NOT gate because both the inputs are tied up. So the output is A. So the answer is D. Right? So D is the correct answer. Divya, any questions or doubts still here?
None.
None. Okay, I move further then.
So it's Dr. Savita sitting with us today as organizing team.
Okay.
Divya was that day.
Okay.
No problem, ma'am.
Okay, Savita, I have renamed you.
True.
So true, na? Okay, so I'll now ask Savita only. Back to your original name. Okay, so for the output F to be 1 in the logic circuit shown, the input combination should be. So they have given us 4 combinations and they say that what we want at the output is a 1. So what should A, B and C be? Now, also I have taken these questions from the net only. And these questions are those questions which have already come in GATE or your net or these kinds of exams. But from wherever I took this site, the answer at that site is wrong. So I've purposely kept their answer, and why that is wrong, I'll explain it to you. First, I'll go by the logic that they are going. Right, so in this circuit, F is, if I give this as D, I label this output as D and this output as E. Okay. F is a 3-input XNOR gate. So of course they have taken it correct. This is a XNOR gate. So this is D, which is the output of XOR gate AB. This is E, which is the output of the XNOR gate, which is also getting inputs AB. And then this is the third input to this XNOR gate. This is right. Now for a 2-value XOR gate, its complement is XNOR, which we can write it in either way, that XOR is the complement of XNOR or XNOR is the complement of XOR. So taking this as, this is the symbol for an XOR gate and circle and a dot is a symbol for your XNOR gate. So either way we can say that XOR is the complement of XNOR, or we can say XNOR is the complement of XOR. So this statement is also correct. If we say A XNOR B is the complement of A XOR B. So either way, the 2 statements are correct. Now what is, this is also correct. This statement is also correct. Right? Why? Whenever you are taking XOR, the XNOR will be complement of it. And an XNOR of it, that means this is the possibility only. right? Because here you have XOR and here you have XNOR. So if XOR will be 0, then XNOR will be 1. And if XOR will be 1, then XNOR will be 0. And now we have to take the XNOR of these two terms. XNOR is an even function, right? Remember, XNOR is an even function. That means when the number of ones in the input sequence is even, then it gives you a high output. And if they are odd, then it gives you a low output, right? So XNOR is an even function, whereas XOR is an odd function. XOR is a odd function. So whenever the number of inputs are as 1 are odd, then your XOR will generate a 1 and otherwise it will generate a 0. So when we'll take XNOR of these two possible cases, the answer will always be 0. It's right. The statement is right. But now what it is doing? It is saying F is 0 XNOR C. This statement is wrong. And why is this statement wrong? Because we saw in the previous case that XOR had the property of associative, right? If you have to make a 3-input XOR gate, you can implement it using 2-input XOR gates. This is A, this is B, this is C. Here we get A plus B, and here we'll get A plus B plus C. Right? So if it is a 3-input XOR gate, what we are doing? We are using the associative property. We are taking XOR of this and then XOR of these two. And that was the reason that a 3-input XOR could be implemented using 2-input XOR gates. But it's not true for XNOR gate. And let's see why it's not true. Sorry. Sorry, I think in the previous I made an OR gate. So if this is A, B, and C. Please don't confuse them with these A, B, and C. So what we have here is A plus B. This is XOR. So we'll write it as this is XNOR. So A, B. This is XNOR means A, B plus A complement, B complement. And then we take it in XNOR with C. So what will this give? This will give A, B plus A complement, B complement, C plus this whole complement AB plus A complement, B complement, whole complement, and with this you take a C complement. Now if you will expand this, you will not get it to a 3-input XOR gate. I'll show it in the table. I have already done that rather than typing it now. So here, this concept is the problem, right? So XOR gate is associative. We can have A XOR B, the way we saw for OR gate. We can have it for XOR gate also, right? So a 3-input XOR gate is associative, but a 3-input XNOR gate is not associative. I have already drawn the truth table. I'll show from there, right? So the problem is in this concept that you cannot take it as associative. Let's come and see this. Right, so I've shown it with the truth table because if we'll do it with the expression, it will be difficult to contemplate the answer. Right, so if I take X, XNOR Y, XNOR Z, this is a 3-input XNOR gate, and use it, the associative property on it. That means we need to first have the column for 3-input XNOR gate. So X, Y, Z, these are the 3 inputs. The 3-input XNOR gate is column output is filled, and I said XNOR is a even function, right? That means whenever the number of inputs, number of ones in the input is even, the output will be 1. So no ones, so output is 1. In this, there are 2 1, so the output is 1. In this case also, the number of ones is 2, so the output is 1. In this case, number of ones is 2, so the output is 1. Of the cases, a single one, that means odd number, so the output is 0. A single one, so output is 0. A single one, so the output is 0. 3 ones, which is also odd, so the output is 0. So XNOR gate is a even function. So this will be the truth table for your 3-input XNOR gate. Now coming to the associative property of XNOR gate. So let's first do X XNOR Y. So we are just doing the XNOR operation of X and Y. The number of ones is 0, so the output is 1. For this case also the output is 1. For these two cases output will be 0, and for these two cases output is 0, and then 1 1 since it is even, so the output is 1. Now do an XNOR of this column with Z input. Okay, that is what we are trying to find out, whether a 3-input XNOR gate can be implemented using 2-input XNOR gates. So when we take this column and this column and do the XNOR operation. So 0 1, it's odd, so the output is 0. 1 1, it is even, the output is 1. 0 0, number of ones is even, so output is 1. 1 0, so the output is 0. 0 0, so the output is 1. 1 0, so number of ones sequence is 1, which is odd, so the output is 0. 0 1, again the number of ones is odd, so the output is 0. This is 1 1, so number of ones is even, so the output is 1. Now compare the two columns. Compare this column which we have evaluated using the associative property, and this column which is by the definition of XNOR gate. And you see that the two are not same. They are not identical. It is in fact XOR. It is a complete inversion of this. We can see. So when we do this, when we want to implement a 3-input XNOR gate, it is not equivalent to like we can add 2-input XNOR gates together. So this is the non-associative property. XNOR gate is non-associative. Therefore, the principle that they have applied in this question is wrong. Right? So this principle that they have applied, that because this will be 0, very true. This will be 0 for a 2-input XOR gate. This will be 0. But we cannot apply this associative property over here. We cannot do like this. This is not done. It will not give us the right answer. So how to handle this question then? Right, so this is the reason why the way it has been solved is wrong. So now what is the correct answer and how to go about it? Right, so coming to this question, we see this was D. Output of gate 1 is labeled D. Output of gate 2 is labeled E. Now this is XOR gate and this is XNOR gate. So this is very true that D and E will always be complement of each other. Right. So now if I see the 3-input XNOR gate, X, Y, Z, where X is D, Y is E, and Z is C. Right. So what happens? This will be treated as D. This will be equated to E and this to C. D and E are coming from 2 gates such that D and E will always be complement of each other. That means these 2 cases can never exist. They can never come. Similarly, these 2 cases can also never come because D and E cannot be same. They cannot be 0, 0. They cannot be 1. They have to be complement of each other. So from the 3-input XNOR circuit, these are the 4 cases that we need to consider. Now, what is the problem? The problem says what should be A, B, C? What should be A, B, and C so that the output F is 1? So that means we are now focusing on this case and this case. These 2 cases we are focusing on when the output is 1. And in for both these cases, we see that the C input should be 1. One thing is clear, that C input should be 1. D can be 0, so E will be 1, or D can be 1, so that E will be 0. Now from where are D and E coming? D and E are coming from A and B. So one thing clear, that C has to be 0. C has to be 1. D and E can be 0 and 1 or 1 and 0. Now if D is 0, D was coming from XOR gate and E was coming from XNOR gate. So this was the XOR output and E was the XNOR output. Now if we see, if I focus on D, which is the XOR output, when will the D output be 0 for a 2-input XOR gate? When both the inputs are same, 0, 0 or 1, 1. And if I see this, that means when will the D input be 1? It will be 1 when A is 0, B is 1, or A is 1 and B is 0. That means we have 4 cases, which basically means 0, 0, 0, 1, 1, 0, 1, 1. That means A, B can be anything. A, B are basically XX, but C has to be 1. Then the output will be 1. Now, what are the options given to us? Options given in the question are this option ruled out, this option ruled out, and this also ruled out. This is the only option given, which is the correct option. Why? Because they have not given all the options, but out of these four, this is the only option for which the function f will have an output of 1. Whereas by the way they have tried to solve it, with that A, B, C, all the three options will give an output of 1, and D is the wrong answer, which is not correct. In fact, D is the right answer and these three are the wrong answer. I purposely took up this question so that whenever you are uh, learning or going through what is on the net, please use it properly, apply your knowledge, and then see whether what they are giving is right or wrong. So the correct option for this is D. C has to be 1. A and B can be anything. Okay. Now the minimum number of 2 input NAND gates required to implement the Boolean function Z is equal to A, B complement C, assuming that A, B and C are available, right? So how many NAND gates are required? 2 input NAND gates. So again, we have to draw the circuit with just 2 input NAND gates, right? So this is a 3 input function. So first thing we need B complement. So for B complement, we need a NAND gate. NAND gate will behave like a NOT gate when both its inputs are tied up. So this gives us B complement. This will further go to a NAND gate to generate A, B complement, complement. So this is A. This also needs to be negated because NAND is also not associative. NAND also does not have associative property. So it has to be again complemented to generate A, B complement. This will then go through a NAND gate, which will generate A, B complement, C, the whole complement. But since the question says A, B complement C only, so this has to further go through a 2 input NAND gate, which will be functioning like a NOT gate. So finally we'll be getting the answer A, B complement C. Right, so we need 1, 2, 3, 4, 5 2 input NAND gates to generate A, B complement C. So if anyone has any questions or you have any specific questions for me to address, please ask. Otherwise, from my end, I'm through.
Ma'am, I think there are no questions till now. I request you all students, please kindly ask the questions or any doubts if you have.
Any doubt related to sequential, combinational, anything? Since we have 15 minutes, we can discuss them. Whatever I can. Savita, are there any questions? Are they asking anything?
Now, ma'am, one question has come up. Akshita is asking, how do we write the formula for XOR gate, 3 input XOR gate?
3 input XOR gate, the formula for 3 input XOR gate, right? So what we have is A XOR B XOR C, right? So if you will see, we'll make the, okay, I have the truth table, I'll go from there only. Right, so this is actually the truth table for your XOR gate. These are the three inputs, and this is the truth table for XOR gate. By definition, XOR gate says what? If the number of ones is even, then your output is 0. If the number of ones is odd, then your output is 1. So this, for this 0, 0, 1, output will be 1. 0, 1, 0, output will be 1. For 1, 0, 0, output will be 1. And also for 1, 1, 1. So now what we can do? We can write this expression in the canonical form. So this becomes, okay, I'll just add a slide. Okay, doesn't matter. So input 0, 0, 0, output will be for XOR gate 0. 0, 0, 1, output is 1. 0, 0, 0, 1, 0, output is 1. Then you have 0, 1, 1, and output is 0. 1, 0, 0, and the output is 1. 1, 0, 1, and the output is 0. 1, 1, 0, output is 0. Sorry. One, 1, 0, output is 0. Then you have 1, 1, 1, and output is 1. So this, the last column is your output column, and the first three columns are your inputs. So let's write it in the canonical form. Please excuse, I don't know why it's taking as a bullet over here. So in canonical form, we have terms 1, 2, then you have 4, then you have 7. 1, 2, 4, and 7. 1, 2, 3 is 0, 4 is 1, 5 is 0, 6 is 0, and 7 is 1. So we write the expression for 1, 2, 4, and 7. So it is x dot y. We are writing in SOP form. So x complement dot y complement dot z. This is 1. Then 2 will be 0, 1, 0. So it is x complement dot y dot z complement. Then you have plus 4 is x dot y complement dot z complement plus and 7 is x dot y dot z. Right? So now what you have, what you can take out common from these two, x complement, y complement, z. Okay, so from the first and fourth term, what we can take out common is z, and from the second and third term, what you can take out common is z prime, right? So this is z dot x complement dot y complement plus x dot y. then you do plus, and we have z complement, and what is inside this bracket is x complement dot y plus x dot y complement, right? So now what you see inside these brackets, this is XOR, 2 input XOR, and this is 2 input XNOR gate, right? So that was the reason when we were trying to implement with XNOR, we were getting a 3 input XOR. So this is Z dot X, this is XNOR Y plus this is Z complement X XOR Y, right? So now if we see this, how is this? This expression related to? This is Z. If I write X XOR Y, if I just write X XOR Y as some expression A is equal to X XOR Y, or say let's say A. So this becomes Z dot A complement plus Z complement dot A, am I right? So, which is nothing but Z XOR A. And what is A? A is XOR X XOR Y, right? So your 3 input XOR is having the associative property, but 3 input XNOR is not having the associative property. Similarly, 3 input AND gate is having an associative property, but 3 input NAND gate is not having an associative property. 3 input OR gate will be having an associative property, but 3 input NOR will not be having, because there is an extra NOT in the circuit in between, right? So if we try to write it like this, 3 input AND can be implemented, right? Because things are not changing. But what happens if we try to write a 3 input NAND in this manner? A negation has taken in between, right? So this will not give you the same answer. Similarly for 3 input NOR, similarly for 3 input XNOR. So these NAND, NOR, XNOR, when we go to 3 inputs and higher, they do not exhibit the associative property, whereas AND or XOR will exhibit the associative property. So a 3 input XOR gate will have this as your canonical expression. Right? So what you have to remember, because normally what is taught is a 2 input XOR gate and a 2 input XNOR gate. But where we say if the inputs are same, then the output is 0, and if they are changing, then the output is 1. But what needs to be remembered is XOR is a odd function generator, right? So it's odd function, whereas XNOR is a even function. That means whenever the number of ones in the input sequence is odd, then XOR will generate a output of 1, whereas XNOR will generate an output of 1 when the number of ones in the input sequence is even. So with this definition, you can write the truth table for whatever inputs, 3 input, 4 input, XOR, 5 input, XOR, or so on. Otherwise, it's very difficult to write the expression. So any more questions?
Thank you, ma'am. There is one more question from Arya.
Hanji.
She's saying, while finding number of gates, how to choose whether we need 3 input or 2 input? In
Well,
one case, In one case, we had taken 3 input, but since it wasn't in option, so we changed.
Yes, because there was no such option. So we had to think of judicially that what is available in the given options, what will be the answer as per that. Otherwise, you will say that the question is wrong. It does not have the right answer. But if we, the catch there was that they should have written how many 2 input gates, but that was the catch, right? So these exams are meant for that purpose only. So that was the catch, that you have to uh, think that whether the question is right or wrong, or what is the underlying something hidden in it which can be utilized. So that's why the answer is 7. If you are attempting it in your theory exam, then whatever you'll write, you will be justifying that 3 input gates will be required, 1, and these many 2 input gates will be required. But in that particular question, it was only a number. So if it is only a number, then we have to think as per the given problem statement. Any more questions?
I think there are no questions further.
Okay, so in that case, I am through from my side. So if I'll stop
So
sharing then.
students, if you have any question, this is the last chance to ask. If there is anything which is not clear, then please do that, ask that just now.
Anything in combinational or in sequential, and that means in digital, anything if you wish to ask, you can ask. I can spend 10, 15 minutes more.
So Dr. Punam Kasturi, we have, as I was telling you, some papers in Delhi University SEC, and they are all completely electronics. So someday we'll have a series of, lectures, because they're like FPGA and, Verilog and things like that.
Yes,
Generally, they are available as DSC papers or SEC papers. And
I think DSC, it is a DSC, FPGA paper, Verilog and FPGA, I think you have it as DSC.
Yeah, either of the two. I was once making a list, and so we need the physics teachers need to know the details of. Okay, so there is another question which says, ma'am, can you explain about 1's complement and 2's complement?
Sure. You see, 1's complement and 2's complement is like we are trying to find.
Everybody, please fill the attendance, because after this we will close it. If anybody has not noticed the chat box, please remember. Yeah.
1's complement is like whenever we are trying to find a complement. Please just give me a second.
Students, please fill the attendance form.
Yeah, I'm sorry. So 1's complement, when we are trying to find, what we are trying to do is that we need to know what is the bit length of the number. So that becomes essential, right? So bit length has to be there. So if bit length is n, say n is 5 or 6 or 7. So let's take it as 4 to begin with as an example. So bit length n is 4. So 1's complement means what we are doing, we are given a number, and that number is subtracted from 2 to power n minus 1 minus 1 and minus x, right? So 2 to power 3 minus 1, 8 minus 1, 7. So what we have, say if this is the number, a 4-bit number, and we want the ones complement of this number. So we'll be just okay, I'll do it here. So what we need to do, we'll be subtracting this 1010 from 1111. Right? So we have to subtract this number, given number x, from 11111. And what is this? I think this just before is 16 minus, yes, this 1 is not there. It's not here, it's here. Right? So 2 to power n minus 1, and from that we subtract this number. And from where is this 2 to power n minus 1? N minus 1 giving us n is 4, then 2 to power n is 16, 2 to power 4 minus 1, this will be 15. Right? So we subtract this 4-bit number from 15. And how is 15 represented in binary? It is represented by a 4-bit 1111. The weight, this is 1 plus 2 plus 4 and plus 8. So 8 plus 4 plus 2 plus 1 gives you 15. So from this we subtract this. So 1 minus 0 gives you a 1. 1 minus 1 gives you a 0. 1 minus 0 gives you a 1, and 1 minus 1 gives you a 0. So a shortcut is that we certainly do not need to all the time do this subtraction. This is the logic behind that, why we are flipping the bits. So to get the ones complement of a given number, we simply flip the bits. So 1 goes to 0 and 0 goes to 1. That is the thumb rule to find out the ones complement. Now to find out the twos complement of the number, the formula is, in general, the formula is 2 to power n minus x. Right? So the formula is 2 to power n minus x. To find twos complement, so again, if I have to find out the twos complement of 1010, I have to subtract this from 2 to power n. N is 4, so this becomes 16. 16 will take 5 place values. And from this we need subtraction. And this subtraction will require a borrow. 0 minus 0 is 0, but 0 minus 1 requires a borrow. Borrow you need to take from the next significant. This is 0, it cannot give a borrow, so it will again borrow, and this will also borrow. So you take a borrow from here, this becomes 0. This borrow comes to this significant, lower significant place. The weight is 2, so 2 plus 0, so this becomes 2. From 2, we give a borrow to the lower significant place. So what remains here is 1. From here, this again 2 plus 0 is 2. You give a borrow to the lower significant place, and what remains here is a 1. So 2 minus 1 is a 1. 1 minus 0 is a 1. And 1 minus 1 is a 0. This is the actual way a two's complement is found out. This is the logic behind. But certainly the working principle, we need not go through this so much. So what we can do is, if the 2 to power n, I subtract 1 and add 1 to it. It will not change anything. I have minus 1 plus 1. This complete becomes 1's complement. So you can take the 1's complement of the number and add a 1 to it. You'll get the 2's complement. So to get the 2's complement, this was the 1's complement. You add a 1 to it, and this becomes this 1 plus 1, 0, carry 1. So this is 1, 1, 0. So you see, we got the same answer. 1's complement plus 1,
So वो webinar
or
चल
by
रहा
the
है,
logic
so
by which we
I'm back.
evaluate 2's complement. Right? So this becomes a more working rule rather than this. This is the principle behind. Now another working rule is what? To find out the 2's complement, you start from the LS bit. If it is 0, you retain it. The first one that you encounter, you retain it. And the subsequent bits, you flip. Again, you get back the same number. So this is how you find 1's complement and 2's complement. So is that clear now?
Thank you, ma'am.
Dr. Poonam, somebody from YouTube had asked that numericals related to multiplexers and decoders, which were not taken in last session. Could you talk about that, or do you think that cannot be done right now?
Just let me see. There were 2, 3. If I can get, I'll just open that. I think it slipped out of my mind. Is my screen visible?
Yes. Yes.
Okay, so the Boolean function implemented in the figure using 2 input multiplexers is what? So we need to find out what is the option, what is the answer. Where is annotate? Right. So this first mux is giving an output of say F1. And if we see what is the output of mux, it depends upon your selection line, right? So it will select one of the inputs and then connect it to the output. So this F1 is B, C complement. These 2 inputs shown inside tells what? If the value of B is 0, then the input selected is C. If the value of selection line B is 1, then the input selected is C prime. So function F1 becomes what? B complement B dot C complement plus B complement dot C. And now this F1 goes as a selection line to the second mux. So F is what? If I say this as B, let me say this X or F1 only. Okay, they're taking it F1 only. So let's take it F1 only. So F is what? F1, when it is 0, F1 complement dot 0. And when F1 is 1, then A is selected. So F is finally what? F1 dot A. And A is what? It's given. What is F1? F1 is B dot C complement plus B complement dot C. Right? So this becomes your complete expression that is being implemented. So this is your option A, B complement C, A, B complement C plus A, B, C complement. So this is your option. For the circuit shown in the following, I0 to I3 are inputs to the 4 to 1 multiplexer, where R is your MSB and S are control bits. So R is your MS bit and S is your control bits. So the output Z will be what? Now, Z is what? I think this should be X here. X or this should be Z. Right? The question output Z. So it should be Z. So Z is what? Z is I naught when R 0, S 0. This should be R complement, S complement. This should not be complete. This is R complement, S complement. Then I1 when P, I1 which is P, I1 will be selected when R is 0 and S is 1. Right? So that's what they said, R as the MS bit. So when R is 0, 0, I0 will be selected. When R is 0, S is 1, then I1 will be selected. When R is 1 and S is 0, then I2 will be selected. And when R1, S1, then I3 will be selected. So this is the basic equation of your multiplexer. So I0 will be selected when R complement S complement. I1 will be selected when R complement S. I2 will be selected when R S complement and I3 when RS. So that's why we said that we keep these selection bits as per the binary expansion of the decimal number. So it becomes easy to write any expression. Right? So this is what I0 is selected when 0, 0. I1 is selected when 0, 1. I2 is selected when R and S is 1, 0. And I3 will be selected when R and S is 1, 1. Now, I0, I1, I2, I3 are connected. I0 is through an OR gate, P plus Q bar. So I0 is P plus Q bar. I1 is P. So it's P over here. I2 is P plus Q. P, and this is an AND gate. So PQ. And I3 is P. So PRS. You expand this. So this becomes PR complement S complement, Q complement R complement S complement, plus PR complement S plus QRS complement plus PRS. So now we have this answer, but this answer is not there in any of them. So we need to minimize it. So we need to put it into a K-map. So PQRS, right? So this is 0, 0, 0, 0. So we are going it in this manner. So S is the least significant and P is the most significant. So when we have P, R complement, S complement, that means Q variable is dropped. So P is 1, P is 1, Q variable is dropped. That means both these rows we are considering R complement, S complement. So R is 0, S is 0. That means the intersection of P and R 0, 0. So these two only. So these two are there, right? So these two we have selected. So these two terms are giving us P, R complement, S complement. Similarly, we need to fill Q complement, R complement, S complement, right? So Q complement, R complement, and S complement. So Q complement will be the first row and the last row. This will give me Q complement. Its intersection with R0, S0. So only this term. We add this term also. So 1, 2, 3 min terms we have added. The third term is P, R complement, S. P, R complement, S. So P is the last two rows. Q will be dropped. R0, S1. So we get these two terms. Then P, Q, R, S complement. We have P, Q, R, and S complement. PQ 1 1. So this row, R is 1, S is 0, R1 S 0. So we have this one. Then the last is PRS. P means the last two rows, R and S means 1 1. So it's the intersection, these two. So we have filled all the min terms in this. Now we need to find out the minimal expression. So this gives me the essential prime implicant because this one has no other way to get grouped. Similarly, this is also an essential prime implicant because this one also has no other way to be grouped. Then I am left with only this option for these two. So without any overlap, we are having three terms, which is, this is PQ. So this is PQ bar. Of course, these are not there because these are four terms and I have made three groups. So three terms, one of them is PQ. This is not here, PQ is here. But let's cross check the rest of the terms also. This will give PQ bar. R will be dropped, S is there. So PQ bar S. And this one will be, P is the variable which is changing its value. So dropped Q bar, R bar, S bar. In fact, all these are wrong. These should be Q bar, R bar, S bar. Right? So this I have taken up from the site only, which gives the answers for gate. So, but this should be Q bar, R bar, S bar. Right? So A is the right answer. So the objective is again the same, that I have to reach to the answer quickly. The very first gave me PQ. PQ is here. It is not there in B. So I just need not worry about the rest. This would be the right answer. But yes, if it's your term examination, then you have to solve your complete answer. So what was this actually? This was, we were implementing a 4 input, 4 variable function with a 4x1 marks. Otherwise, if I simply take a 4x1 marks, we could implement a 2 variable function, at most a 3 variable function. But here we are implementing a 4 variable function. So what we are doing, the most significant, these two are given to the selection lines, and we are finding out the inputs. In this particular example, the inputs are already given, so we are trying to find out the function. This is also on the same lines. It's a 4x1 mux, which is a 4 variable function, implementing a 4 variable function. So the two selection lines S0, S1, they are given A, B. So these are the most significant terms. And then the rest of the variables are used to generate I0, I1, I2, and I3. The basic again remains the same. The basic equation for your multiplexer, that I0 will be selected when S0 is 1 and S1 is, I0 will be selected when S0 is 0, S1 is 0. I1 will be selected when S0 is 0 and S1 is 1. So they have taken actually, while doing this, S0 as a higher significant variable, but normally S0 is always treated as a lower significant. So I1 is 1 0, selected on 1 0, and I3 is selected on 1 1. It as per me, Hanji.
Would you with this be your last one of the last numericals?
Yes.
If there are more, you are most welcome to share it with us. We share it directly to the students also.
Sure. This will be the last one. This is the last one.
Because generally they have 3.5 hours is a bit too much.
I understand. Yes, I understand.
Okay.
Had I just it slipped from my mind, otherwise I would have covered it previously only. Okay, so as per me, I1 should be this, but the way right now the solution is going on I'll go with the flow. So we are taking S0 as the higher significant and S1 as the lower significant. So this is how you are getting the expression for F. I0 can be substituted, it is C. I1 can be substituted, it is D. I2 can be substituted, it is C complement. And I3 can be substituted as C complement, D complement ka it's AND product. That means what will it give? It will give C complement dot T complement and of it. Right? So these bubbles indicate a NOT gate. So these bubbles indicate a NOT gate. So the inputs are complemented. So this basically becomes C plus D. Right? So this becomes C plus D. So by substituting these values, you can find out and then correlate them to your multiplex minterms. This will expand into your canonical form. Once you have it in the canonical form, you can term it in your minterm expression, and then you can find out whatever answer you are getting correlated with the terms. So with this, I rest my presentation now. And if you have any questions or queries, you can always write me on my email ID.
Yeah. So students,
Thank you so
I
much.
think it was so nice. And Dr. Poonam, I request you to share your PPT, because if this PPT is not shared, the students keep on asking us, when will
Sure,
the
sure.
speaker
I'll do
share
that.
the PPT with us?
Sure,
Because
I'll do that.
I understand this. Sometimes the voice of the speaker, then what it was said while showing this, gets linked together and enhances the memory. So you remember things if you have some sound along with it. It helps. To many brains, it helps a lot.
I'll do that. I'll
So, so
certainly share
please
it.
share the PPT with us. And if there are any questions of any students, you can pass it on to me and I will ask Poonam ma'am. Thank you so
Sure.
much, ma'am,
My
for
pleasure.
agreeing for this lecture and giving it so patient a hearing, explaining everything. And the best part was pointing out how to arrive at the answer without taking a very long route, and how to assess if your answer is not nearing any of the options given in the question paper. That really requires some insight. Thank you so much.
My
It
pleasure.
was a pleasure. And I request Dr. Savita to kindly stop the live recording, the local recording, and then end the meeting. Thank you.